In this video, I'll explain order of elements in Sn. How to find order of any element in Sn. You know that any element in Sn is nothing but it is a permutation. I will name that permutation as sigma. And if you have any permutation of Sn, every permutation you know that it has a cycle decomposition. You can write it in a cycle decomposition form. Every permutation can be expressed as product of disjoint cycles that you already know. So due to which it has some cycle decomposition, means it may be a product of 2 cycles, 3 cycles, 4 cycles, combination of all those. Suppose if it has the cycle decomposition in this way, the length of the cycle it is, then order of that permutation is nothing but LCM of n1, n2, so on up to nk. I'll illustrate this with an example. Just wait. See, one more fact you have to remember: the number of distinct cycle decompositions of permutations in Sn is same as number of partitions of natural number n. See, let me take one example. S3. Okay, here n equal to 3. Which are the partitions of 3? So partitions of 3 are 1 comma 1 comma 1, trivial partition, then 1 comma 2, then one more is 3. There are 3 partitions of n equal to 3, p of 3 equal to 3. The cycle decompositions of permutations in S3 is also 3. Means there are 3 types of cycle decomposition. One is identity, another is 2 cycle, another is 3 cycle. That is in this way. So S3 has identity. Identity is nothing 1 comma 1 comma 1. Next 1 comma 2 means 1 2, 1 goes to 2, 2 goes to 3, 1 goes to 3. So these are transpositions. Transpositions will have cycle decomposition 1 comma 2 because one element is fixed, another element is of length 2. Okay. Next, it is of length 3 cycle 1 2 3 1 3 2. These are elements of S3. Therefore, number of distinct cycle decompositions of Sn is same as number of partitions of n. Hope this point is clear. So here there are 3 distinct cycle decompositions. One is this identity, another is transpositions, and one more is 3 cycle. Transpositions means 2 cycle and 3 cycle. Similarly, you can check with S4. See in S4, n equal to 4, what are partitions of 4? Partitions of 4 are 1, comma 1, comma 1, comma 1, then 1, comma 1, comma 2, 1, comma 3, then 4, then 2, comma 2. There are 5 partitions of natural number 4. Therefore, there are 5 distinct cycle decompositions in S4. One is identity, one is transposition, 2 cycles, then you have 3 cycles, then you have 4 cycles, then you have product of 2 cycles, product of 2 transpositions. That is like this: S4 has identity, then you will have transpositions 1 2 1 4 3 1 4. I will not list out all. Then 1 3 means you have cycle of length 3 1 2 4, like that. Then you have cycle of length 4 1 2 3 4. Then you have 1 2 3 4, like this, product of cycles of length 2. These are the possible cycle decompositions in S4. Other than these 5, you don't have any other possibility. So this fact you have to remember: the number of distinct cycle decompositions of permutations in Sn is same as number of partitions of n. Therefore, this idea gives you the number of possible orders of any element in Sn. See, consider S3. Let me take S3. Okay, S3 has 6 elements: identity 1 2 1 3 2 3, then 1 2 3, then 1 3 2. Okay, these are the 6 elements of S3. Now we have to find out possible order of any element of S3. S3 has 6 elements. Now possible order of any element in S3 is nothing but, what is order of any permutation? It is LCM of cycle decompositions, correct? No. So first you know that cycle decomposition is the same as number of partitions of n. So what are partitions of 3? Partitions of 3 are 1, 1, 1, then 1, 2 and 3. Okay. What is their LCM? LCM is 1, 2 and 3 here. Therefore, what are possible orders of any element in S3? 1, 2, 3. Other than these three numbers, you can never get any other number as order of element. Suppose if I write order of 1, 2, this is an element of S3 as a 4, then this is wrong, because possible order of any element of S3 is 1, 2, 3, because that only comes when you take the LCM of these cycle decompositions. Therefore, now 1, 1, 1. This is the cycle decomposition of identity permutation. Therefore, order of this identity permutation is always 1. Next, take up this cycle decomposition 1, 2. That belongs to these three transpositions. Therefore, order of 1, 2, order of 1, 3, order of 2, 3 all equal to 2. Next, order of this 1, 2, 3 as well as order of 1, 3, 2, that is equal to 3, because the LCM, cycle decomposition's LCM is 3. Therefore, this is how to get the order of elements in S3. Similarly, let us find out for S4. Now let us consider S4. First let us find out what are possible order of any element of S4, which is nothing but LCM of cycle decompositions. Cycle decompositions of S4 is same as partitions of 4. What are partitions of 4? See, let us write partitions of 4. This is the first partition 1 comma 1 comma 2, then 1 comma 3, add these two, then 1 plus 3 it is 4, one more cycle is 2 comma 2 by adding these two together 2 comma 2. These are the cycle decompositions. They are nothing but partitions of 4. Now take LCM 1, here LCM is 2, here LCM is 3, LCM of these numbers 4, and here LCM is 2. Correct. Now, therefore, possible order of any element is nothing but 1, 2, 3, 4. So S4 has how many elements? 4 factorial elements. The S4 has 24 elements. Correct. No, 24 elements are there in S4, but possible order of any element in S4 is 1, 2, 3, 4. No other possibility will arise for order of element of S4. So, what is maximum possible order of any element in S4? It is 4. Similarly, in S3, it is 3. So, maximum possible order is also calculated using this. Now, after getting LCM, look at the elements now. Only identity has a order 1. Then, see, permutations with the cycle decomposition 1, 1, 2 and cycle decomposition 2, 2 will have orders 2, and permutations with the cycle decomposition 1, 3 means 3 cycles. 3 cycles permutation will have order 3, 4 cycles permutation will have order 4, and product of 2 transpositions and transpositions will have order 2. So, for example, order of 1, 2 is equal to 2, order of 1, 2, 3, 4. This is an element of S4. This element's order is also equal to 2, because these two cycle decompositions will have same LCM. So order is nothing but LCM. Therefore, these product of transpositions will have order 2, and single transposition will have order 2. Any cycle of length 3, 1, 2, 3 like this, that will have order 3. Then any cycle of length 4 will have order 4. Means sigma of 4 equal to identity. Correct. Now, what is order of an element? A to the power 4, a to the power n equal to e, where n is the least positive integer. So, in this case, sigma power 4 equal to I for this fourth cycle. then that is called as order of that permutation. So this is how to get possible order of any element and order of an element in Sn. In the next video, I'll explain how to find number of elements of order k in Sn.